Hello everyone. Today we are discussing waves. This is a very math heavy topic. We're going to solve some equations with complex exponentials. So feel free to skip this video if you're not interested in equations, but otherwise feel free to follow along. We'll actually use this in probably the next video, but for this video we're doing only math. So first of all, let's just say we are recording a microphone and we have some sound that the microphone is recording for us. Maybe somebody's playing a piano, or maybe you're playing a violin or something like that. And the task is, well, we know what the frequencies of all the piano notes are, and we would like to just transform what we hear with the microphone into what are the frequencies that are present so that we can analyze the sound, so that we can figure out what note the person is playing. Well, you can use a whole set of different transforms. I guess maybe just one transform in different forms, but what you do is we can take the FFT or the DFT, but what we will do, essentially we'll do a DFT, discrete Fourier transform, but we won't use the same coefficients, we won't use the same frequencies that the Fourier transform does, we will use the piano note frequencies. In order to be able to do that, we need to write a filter that takes a note frequency, that just takes a frequency, and it gives us the amplitude of that, or the coefficient of that frequency. So yeah, in the input signal. Which, before we even do that, let us write what the input signal is. We know that a wave, just any wave, is a complex exponential with the coefficient up front is the amplitude of the wave, and then the exponent is going to be the phase. But the other thing that we need to keep in mind is the signal has multiple frequencies. When you play the note A on the violin, you don't have just one frequency, you have the fundamental frequency, and then you have a bunch of harmonics. So not only do we need to filter for different notes, but also we need to filter for the harmonics, but luckily we can do all of that with just one set of frequencies that we can iterate over in a computer program, and we can have the computer do this for us and blah blah blah. Okay, yeah, I like making the computer do the work for me, but before we make the computer do the work, we need to figure out what exactly, because the computer doesn't take, we can't just tell the computer, hey, give me this, right? This is not like, unless the computer is pre-programmed for us, which it's not in this case. So what we need to do is we need to first put what we need into an equation so that we can program the computer, because the computer can understand equations and it can do work for us if we give it some equation to work with. But we need to come up with the equation ourselves, and that is why math is important. Yeah, if you do programming. Now, the nice thing is oftentimes you already have the equation on the internet somewhere, but in this case the equation is simple enough that we will do it ourselves. So let's start out by writing what a signal is. Signal, we'll use lowercase s to express the sound signal. Small t is the time at which we're measuring the signal. So this is equal to the sum, and we'll use small n equals 0 through big N. So the n represents which component, because if we have all these harmonics, everything, so small n represents just which component of the signal that we're looking at. Now there we also have, so we have the big A, that's amplitude sub n, so each component has its own amplitude. E to the I, we'll say phi sub n of t. Now phi sub n is going to be our moving phase, and so the components that have a higher frequency will have the phase move faster, and we can use that. It's just easier to express in this equation, and phi sub n is equal to 2 pi frequency times time plus phi naught. Now the frequency depends on which component we're looking at, so we'll say frequency sub n and phi naught is also sub n. So each component of the signal has its own parameters for the wave equation. All right, so we have a defined signal here. What we want is, the goal is to extract the frequency coefficient, or the Fourier coefficient, that frequency spectrum coefficient that we want for the frequency, because we will have a set of frequencies, one frequency for each piano note, and actually we'll do frequencies in between the notes too, just in case the note is out of tune. We want to be able to tell that, so we'll do that. And then in order to do this though, we need to write a filter where first of all, I'll say S prime of t is equal to S of t times e to the minus I. We'll call it delta phi. So what this does is this S prime is actually a transformed. Now, what we want to do is we want to do delta phi of t. And then the delta phi of t is equal to 2 pi f naught t. We have some frequency f naught that we are interested in extracting the coefficient for. We want to know how much of this frequency is in the signal that we are looking at. But in order to do that, we first use this in order to frequency shift the input signal so that the output is some signal that is centered over the frequency that we want. So in other words, if we had some frequency that is input at, say, 10 kilohertz, then we frequency shifted by minus 10 kilohertz, then whatever signal was present at 10 kilohertz, whatever signal was being carried by 10 kilohertz, it is now at 0 kilohertz. So now all we have to do is average out the noise, which in this case all the other frequency components are noise for us. So now we just have to average out the noise, and that gives us the signal at 0 kilohertz, which is actually the signal that was at 10 kilohertz before we downshifted. So we can determine what is at 10 kilohertz by doing this. And I'm just going to rename this f naught to f sub m actually. So we have labeled everything with m that needs to be labeled with m, and then we can say coefficient at m is equal to the integral from some t naught to some t naught plus delta big T of s sub m prime of t with respect to t. And we can optionally divide that by delta big T, but we're not going to, just because it's all relative and we don't care, we just care about the empirical. But if we do the math here, then we can figure out, so coefficient sub m is equal to integral from t naught to t naught plus delta big T of the only term that will actually matter after we average this out using the integral is the term with the correct frequency will matter. The other terms will pretty much cancel out. We'll have a little bit of noise left. So we have a sub n times e to the I 2 pi f sub n t plus I times phi naught sub n times e to the minus I 2 pi f sub m times t dt. And that's equal to integral t0 to t0 plus delta big T of a sub n. So where we have whenever we have f sub n is not equal to f sub m, then these terms will have some oscillation to them. The resulting expression will be a wave, and so when we average over delta big T, the result will be fairly small. Whereas when f sub n is equal to f sub m, then we will have the resulting, the waves will subtract from each other because of the properties of exponents, and we will just be left with the phase. So I phi 0 n dt, and then so this is equal to, this is just a constant now, nothing depends on t anymore, and so we just have the delta big T times a sub n times e to the I phi naught n, and this is equal to c sub m, and actually plus noise, we'll say that. So this is kind of cool. It would probably take a lot longer to explain like the intermediate steps that I took here, but that's, if you do the math, it works out fine. You can find the coefficient of some frequency by doing this, and actually the equation that will help us even more, because the thing is we don't know what this coefficient is, but we are able to, what we can do is we can do the sum over t of the signal at t times e to the minus I 2 pi f sub m, and what that does is it gives us an expression that we can evaluate that'll give us the coefficients, and all we need is the signal, which we have the microphone, and we need a complex exponential with the frequency that we want. And that gives us the coefficient for that frequency, so we have to just repeat the same process for all the frequencies that we're working with, and that gives us the picture, so we can determine what notes are being played and if they're in tune or not. An application of this is we could make an instrument tuner. We could also make an app that perhaps tells the person, say they're practicing violin and they're off tune, it'll tell them if they're off tune or not, ideally. And then the other application of this is we can make a transcription software, possibly perhaps, that can take the input, that can listen to someone play some music on an instrument and can maybe write some notes. So we'll see what we can do with this. But this has been the math behind waves and finding frequency spectrum coefficients.